Hello friends, welcome in a lecture of fluid mechanics subject. Myself Mitesh Patel and I am working as an assistant professor in a mechanical department at a Dr. Subhas Technical Campus, Junagadh. Today's our lecture topic is a hydraulic gradient and total energy line. In this lecture we discuss about the what is the hydraulic gradient and hydraulic gradient line and what is the total energy line and how to draw it and how to get it from the energies and piezometric head and total energy head. Okay, so let's start the lecture. First we see the total energy line. Okay, as per the name total energy, so we first find out the total energy, and in hydraulic subject we also call the total energy as a total head. So we find out the first total head. So in this total head we know that the total head is the sum of potential head or elevation head, pressure head and velocity head. So mathematically total head or total energy is equal to potential energy, pressure energy, potential energy and velocity energy or kinetic energy. Okay, so this is the pressure energy or pressure head, P upon rho g or specific weight. Z is the potential head or potential energy, and V squared upon 2g is a kinematic energy or velocity head. Okay, so this is the mathematically we represent the total energy and total head. Now when the fluids flow along the pipe, there is a loss of head and total energy of fluids is decreased in the direction of flow. When the fluid is flowing into the pipe, we know that there are many losses as a friction, as a expansion, as a reducers and any other bends and any other pipe fittings. These all losses reduce the total energy of fluids and decrease the total energy of fluid. Okay, if total energy at a various point along the axis of pipe is plotted and joined by the line so obtained is called the energy gradient line. Okay, in short we can say that at a various point we find out the total energy through the reference of axis of pipe and join these points and line we get the line. This line is called the energy gradient line. Okay, in literature energy gradient line is also known as a total energy line. We know that why we say the total energy line. It's a line of the various point of total energy, so that's why we call the line is a total energy line. Okay, so it's a same things, energy gradient line and total energy line is a same. Okay, now next is the hydraulic gradient or hydraulic gradient line. Okay, now the sum of potential head and pressure head means potential energy and pressure energy at any point is called as a piezometric head. Okay, so piezometric head given the hydraulic gradient line. Okay, what is the piezometric head? It is the sum of pressure energy and potential energy. Now if the line is drawn joining the piezometric level at a various point, the line so obtained is called the hydraulic gradient line. Okay, hydraulic gradient line is a line which is passed through the piezometric level at a various points. Okay, ready? Now some important points about the hydraulic gradient line is discussed. First one is the energy gradient line always drop in the direction of flow. the hydraulic gradient line is always drop or downward direction, or the direction of flow, it's a downward side, is drops. Why? Because of the losses. We earlier discussed that losses happens in the flow of or pipes or any other there, because of the friction and any others fittings of pipes. Okay, that's why the energy gradient line is always drop in the direction of flow because of the loss of head or loss of energy. Okay, second one is the hydraulic gradient line may rise or fall depending on the pressure changes. Okay, if the pressure is changes, according to that hydraulic gradient line is rise or fall. Not always it's been fall. It's obey or follow the pressure energy. If pressure energy or pressure is high at some point, then hydraulic gradient line is also rise. Okay. Now hydraulic gradient line is always below the energy gradient line. If this sentence is say that hydraulic gradient is lower than the total energy. It's always happen because in hydraulic gradient kinetic energy is not considered. That's why the hydraulic gradient energy is always less the total energy. So always hydraulic gradient line is always below the energy gradient line. Okay, and the vertical intercept between the two is equal to the velocity s. In short, this line is said that the vertical distance between the hydraulic gradient line and energy gradient line is equal to the velocity head or kinetic energy. Okay, the distance between the two line, hydraulic gradient line and total energy line, is equal to the velocity head. Okay, distance is equal to the velocity head between these two lines. Now next is for a pipe of uniform cross section, the slope of hydraulic gradient line is equal to the slope of energy gradient line. Okay, for a uniform cross section, we can say that the hydraulic gradient line and total energy line is parallel, so the slope is equal in both. Okay, when the uniform cross section is there in a pipe. Particularly, there is no relations whatsoever between the slope of the energy gradient line and slope of the axis of pipe. Okay. Okay, these points are important for the hydraulic gradient line, and this point is also noted that in the analysis of hydraulic gradient or piezometric head or to draw the hydraulic gradient line. Okay. Now see the problem, how to draw the hydraulic gradient line and total energy line. So discuss about the datas. First see the data, which data is given. A horizontal pipeline 40-meter long is connected to the water tank at one end. Okay, the horizontal pipe is connected at one end of water tank, and the pipe length is 40-meter long. Okay, now and the discharge freely into the atmosphere at the other hand. For the first 25 meter of its length from the tank, the pipe is 150 mm diameter. The first 25 meter length of pipe having a diameter 150 mm diameter. Okay, and its diameter is suddenly enlarged. The pipe diameter is suddenly enlarged after the 25 meter from the tank connected joint. How much enlarged is 300 mm, enlarged to 300 mm, diameter is enlarged to 300 mm. the height of water level in the tank is 8 meter above the center pipe. Okay, center of pipe, the height of water level in tank is a 8 meter. Okay, so height of water is a 8 meter. Now considering the all losses of head which occur, okay, first determine the rate of flow, and second draw the hydraulic gradient line and energy gradient line. Okay, take AF is equal to 0.01 coefficient of friction. Okay, 0.01 is a given for the both section of pipe. This is a constant for any section of pipe. Okay, now length is given. Total length of horizontal pipe is a 40 meter. First section of pipe is length is a 25 meter. Second section of pipe length is a 15 meter. Now first section pipe diameter is a 50 mm and second section diameter is a 300 mm. Okay, now height of water is a 8 meter and coefficient of friction is given 0.01. Okay, now we have to first find out the discharge or rate of flow. So we know that the equation of rate of flow or discharge is a AV. So we have to find out the discharge at the exit of pipe. So it's A2 V2. So we have to find out the velocity at the exit, that means the V2. Okay, so we know that how to find out the V2 with the help of Bernoulli's equation. So first we apply the Bernoulli's equation at the two section. First section is considered as a free surface of water in a tank and other section is considered as a outlet or exit of pipe. This is the two section where the Bernoulli's equation is applied. Okay, so we know that in a Bernoulli's principle, total energy at a section 1 is equal to the total energy at a section 2. So in total energy, three energies is there: pressure, velocity and potential. Three head is there at a section 1, three head as a section 2. But at a section 2, what is there? Losses is there. Okay, so losses is considered in a section 2 due to the fluid is flow from this section to this section. The losses is there. So losses is considered at a section 2. Okay, now at a free surface of tank, it's open in a free atmosphere. So atmospheric pressure is a datum. So gauge pressure is 0. So pressure head or pressure energy is a 0 at this section. Okay, now the water tank surface or free surface of water having a velocity is a very negligible velocity. So it's also considered as a 0 velocity head or kinetic energy of free surface. Okay, the only height or datum head or potential head is a 8 meter as shown in figure. So only potential energy is a 8 meter. Okay, potential head is a 8 meter for a free surface of water. The other one is a 0 for a free surface of water. Now for a other section, consider at a outlet of pipe or exit of pipe. The pressure head P2 upon rho g or P2 upon specific weight, velocity head V2 square upon 2g, potential head Z2, and all losses which are occurs in this flow in different two section of pipe. Okay, first pressure energy is 0 because at outlet of pipe the flow is free, so free flow not having the pressure, and the datum is 0 at a section 2 because we consider the datum line or reference line is a center pipe of pipe, and the datum height is at a section datum height is a 0. Okay, so potential energy or datum head is 0. Okay, so only section 2 having at a section 2 the fluid having only kinetic energy or velocity head V2 square upon 2g. Pressure is 0 because of the flow is free out at a exit free flow of fluid. So pressure energy is 0, and the datum height is a 0 because the reference datum is a center axis of pipe. So datum difference is a 0 at a section 2. Okay, so both are 0. Only velocity head is there. Now in losses, what losses are considered? First is the entry losses. Okay, so first one, loss of head due to the entry of pipe or inlet of pipe. Then friction losses at a section 1, HF1 head loss due to the friction at a section 1, HF1. Now at a sudden expansion, so head loss due to the sudden expansion, and last loss is the friction at a section 2, HF2 head loss due to the friction at a section 2. Okay, so all losses are considered for section 1 and section 2 of pipe. Okay, now from that equation we find out the velocity V2, but we have find out the all loss of heads. So first, loss of head at a entrance or inlet equation is a 0.5 V1 square upon 2g, we know that, and the friction head or friction head loss is find out the by Darcy equation for FL V square upon 2GD, we know that. Now at a sudden enlargement or sudden expansion, losses are find out with this equation, we know that V1 minus V2 in bracket square upon 2g. Okay, now another friction loss for a section 2, we know that, find out with the help of Darcy equation for FLV square upon 2GD. Here velocity, diameter, R and length is considered for a section 2 of pipe, and here length, velocity, diameter is considered for the section 1 of pipe. Okay, now applying the continuity equation at a section 1 and section 2 of pipe. So A1 V1, A2 V2, A1 V1 is equal to A2 V2 as per the continuity equation. Now get the value of V1 through this relation of continuity equation. So V1 is equal to A2 V2 upon A1. Now put the value of areas. The area equation is a pi by 4 d square. So A2 is a pi by 4 d2 square, and A1 is a pi by 4 d1 square. Pi by 4 is a cancel. Now in bracket d2 upon d1 square bracket square into V2. Now we have a diameter of both section of pipe, so put the value of all both diameter and get the relation between the V1 and V2 is the V1 is equal to 4 V2. Okay. Now get the all head losses value in form of V2. Okay. First H1 or H inlet 0.5 V1 square upon 2G. Now we have a V1, put the value of or put the equation of V1 in form of V2, put the value of V1 in form of V2, it's a 4 V2 square, and finally we get this for a head loss due to the inlet. Head loss due to the friction, we put the all values, friction coefficient, length L1, and value of V1 is a 4 V2. Okay, and finally we get the 106.6 V2 square upon 2G for a head loss due to the friction for a section 1. Now sudden enlargement V1 minus V2 square upon 2G. So here put the value of V1 in form of V2. So we get the 9 V2 square upon 2G, and here HF2 means the head loss due to the friction for a section 2 of pipe. Here length, velocity and diameter. Here V2, so not the any kind of value is good. We take the all values in form of V2. So here we get the value 2 V2 square upon 2G. Okay. Now in Bernoulli's equation, we put the all values in form of V2 of all head losses are placed as shown in slide, and all the values are known excepting the V2. So we get the value of V2 from this relation, and we see that we get the value of V2 1.11 meter per second. Okay. Now rate of flow Q is equal to A2 V2. We know that we have an area of A2, and now we find out the V2 velocity at a section 2 or outlet is a 1.11 meter per second, and we finally get the discharge. Okay, its discharge is a 0.078 meter cube per second. Okay, now we find out the second one. It's the hydraulic gradient line and energy gradient line we have to draw. So first of all, first we have to find out the all losses values. Now we have a V2 value of V2, so put the value of V2 in this above equation, and finally we get the value of all the head losses due to the inlet, head losses due to the friction at a section 1, head losses due to the enlargement sudden, and last one is the head loss due to the friction at a section 2 in pipe. Okay, so we find out the all values here, putting the value of V2 in the above equation. Okay, earlier find out equation. Okay, now we draw the energy gradient line first. Okay, step by step. Firstly, we know that the point L lies on the free water surface. At a here free water surface at a L point, the energy is a 8 meter or head is a 8 meter. Okay, now the fluid is inlet into the pipe. So due to the inlet, we know that the head loss due to the entry or inlet is a 0.5 meter in a head. So head loss is a 0.5 meter. So total head is decrease. How much decrease? 0.5 meter is decrease. So Lm is a 0.5 meter. So energy is decreased by, or energy head is decreased by 0.5 meter. So draw the Lm line. Okay. Now from M, draw the horizontal line MA. Okay. As shown in figure here, equal to the length of pipe as a section 1 L1. Okay. Now draw a vertical line downward from the A point. How much? As the HF1. What is the HF1? It is the head loss due to the friction at a section 1 of pipe. Okay. So head loss due to the friction at a section 1 of pipe is a 6.7 meter head loss. Okay. So from A point, draw the 6.7 meter downward line and get the point N. Okay. Now join the M point and N point. So we get the MN line as shown in figure. Okay. Now from N line, we know that here the section is changed, diameter is changed, the diameter is increased. So head loss due to the sudden enlargement is occurs at this section. So head is further decreased due to the sudden enlargement. How much decrease? 0.56 meter. So here NS line length is a 0.56 meter downward because the head is lost due to the sudden enlargement. So line is a downward. NS how much length? 0.56 meter. Okay. Now we get the S point at the end of line 0.56 meter. Now draw the SB line horizontal as shown in figure from the S point. Okay. Equal to the length of pipe L2. Now draw the line from B downward direction to equal to the head loss due to the friction HF2 at a section 2 or for a section 2. How much? 0.126 meter. So here from the B point, draw the downward line. How much line? Length is a head loss is a 0.126 meter. So the line length is a 0.126 meter and we get the T point at the end of line. Okay. And join the S and T point. And we get the total energy line from L to T point. So LM, M to N, N to S and S to T, it is the total energy line or energy gradient line. Okay. I hope you all understand very well how the total energy line is draw or get. Okay. Now we see the hydraulic gradient line. How we get? Hydraulic gradient line is how to get, we discuss. From the M, we take the 1 meter down. Why? Hydraulic gradient having energy or sum of the energy of pressure energy and potential energy, not considering the velocity head or kinetic energy. So 1 meter is minus from the total energy line. So from M we minus the 1 meter and draw the downward direction line in length of 1 meter because the head is lower than the total energy and piezometric head. Difference is a 1 meter of a velocity head. Okay. That is the difference of velocity head, 1 meter between them, M and P point. At the P point is a piezometric head and M point is a total head, and the difference between them is a velocity head. Okay, it is a velocity head. If velocity is add, then the total head is get. We have now PQ line is parallel to MN line. Now draw the PQ line, the length of MN line parallel to MN. Okay. Now next, from the U point, the U point is the center line of the end section or end cross section of pipe. Why? At the free end or a free section, we considering the energy, the pressure energy is 0 because of the flow is a free after that section, so pressure energy is not considered, it's a 0. Datum or potential energy is 0 because the center line is also considered as a datum line, so not a distance between the datum line and potential head is a 0. So only velocity is head there or kinetic energy is there in the flow, but is not considered in the hydraulic gradient line. So at the outer section or at a outlet, the always hydraulic gradient line at a center point of cross section. Okay, so U point is a center point of the cross section. Now draw the UQ line parallel to ST line. Our length is similar. Now join the V and Q point, and now we get the line, hydraulic gradient line, PQVU. PQVU as shown in figure. This is the hydraulic gradient line. So first we have to draw the total energy line, and from the help of energy line we easily get the, in 2 to 3 steps we find the hydraulic gradient line. After subtracting the velocity head from that, easily we get the hydraulic gradient line from the total energy line. So always first draw the total energy line and then hydraulic gradient line. Okay, I hope you very well understand the concept of hydraulic gradient and total energy line, and you also learn the how to draw the hydraulic gradient line and total energy line. Thank you. If you have any questions regarding them, then feel free to ask to me. Okay, thank you again.